This is Jennifer Martinez, and welcome to Cramer's Rule. Cramer's Rule is another method for solving systems, like the system that you see here in example 1. We have learned many methods for solving systems. In past classes, you learned elimination and substitution. In this class, we used matrices, row reduction, using echelon form to solve systems, and we also used inverses to solve systems. In this, Cramer's Rule is going to use determinants. I'm just going to start with reading the first paragraph here. Cramer's Rule is needed in a variety of theoretical calculations. For instance, it can be used to study how the solution of ax equals b is affected by changes in the entries of b. However, this formula is inefficient for hand calculations except for 2x2s or perhaps 3x3s, because finding determinants of larger matrices does become a little bit more challenging. So let's start. So before we go to the theorem, or what Cramer's Rule is, they have a new notation definition. It says for any n by n matrix A and any b vector b in Rn, and again it has to be an n by n matrix, we're going to let A sub I of B be the matrix obtained from A by replacing the column I by the vector B. So we literally take the matrix A, and instead of the ith column, you replace B. There's the B. So what Cramer's Rule is we're going to then find the solutions by taking the determinant of that new matrix divided by the determinant of the original matrix, A. So it says here, let A be an invertible n by n matrix. For any b in Rn, the unique solution x of ax equals b has entries given by this. That's all that it is. So let's look at example 1. We're going to use Cramer's Rule to solve the system, and we're going to let A be the coefficient matrix. So A sub 1 of B, what is that? We're going to take this B, this 6, 8, and we're going to replace it for the first column. So instead of 3, negative 5, we're going to put 6, 8, but we're going to leave the second column. And A sub 2 of B is the same idea. We're going to put it in for the second column. So again, leave the first column alone and change the second column. And then you just use this formula. So the determinant of A, let's look at that. What is the determinant of A? It's equal to 12 minus 10. So that's 2. So they said since the determinant of A is 2, you're going to, and the determinant of, we're going to take the determinant of A sub 1 of B over the determinant of A, and then the determinant of A sub 2 of B over the determinant of A, and you're going to get the answers. You can check them to see if they're right. Another notation for this, sometimes I use, is this x1 is equal to, I just write what it is. Again, I'm going to put the 6, 8 in the first column, and then negative 2, leave the negative 2, 4 alone. We know that's a 2, and that's where they got 24 minus a negative 16. That's where they got the 20. And then the x2, again, it's going to be the determinant. Leave the first column like it is, but instead of the second column, I'm going to write that 6, 8. And then find the determinant of that, which is 24 minus a negative 30. So that's why they got 24 plus 30 there, divided by 2. So let's do the same thing, number 5 in the book, with a 3x3. So first I'm going to look at the determinant of A, where A is that coefficient matrix. So A is just going to be the 1, negative 3, 0, 1, 0, 1, and 0, 2, negative 2. And I'm going to determine this determinant. So what would that be? We could do a little row reduction, multiply the first row by 3 and add it to the second just to make our lives a little bit easier. So that would be 0, that would be 3, that would be 2. Leave the second one alone. And I'm going to go ahead and use that first column to get 1 times the remaining. If I cross out the first column and first row, I end up with 3, 2, 1, negative 2. And I'm just going to say the determinant of A is therefore negative 6 minus a 2, negative 8. And then I'm going to look for x1. And we know it's the determinant of a1 of b all over the determinant of a. And I'm going to write that as the b is 3, 0, 2. So I'm going to put that in the first column. I'm going to leave the second column alone. And I'm going to leave the third column alone. So I can say where b is equal to 3, 0, 2. So that's what a1 of b is. And we know this one's negative 8 already. So I'm just going to figure that determinant out. That second column looks nice and easy. Or second row, I mean. So I'm going to take that 2, and then that's a plus minus 2. And I'm going to cross out that second row, third column, and get 3, 1, 2, 1 left. And I just figure out that. That would be 3 minus 2. So it looks like the answer is 1/4. So x1 is 1/4. So x2. By the formula, it's the determinant of a2 of b over the determinant of a. Again, we take that b and replace it by that second row. So I'm going to leave the second column, I should say. The first column alone. Make the second column 0, 3, 0, 2. And the third column I leave alone. That should be a negative 2. And we know that is a negative 8. And I'm going to get a 0 in that position right there. So what would that be? That would be 0, and then 9, and 2. And if we then use, it doesn't change the determinant. So the answer is going to be 1 times negative 18 minus 4. Which is negative 22 over negative 8, or 11 over 4. So finally, let's do x3. Need more space. So x3, we know is the determinant of a3 over b, over the determinant of a. So again, we're going to leave the first 2 columns alone and replace b, that last, with the last column. And the determinant of a is still negative 8. And that second row looks nice and easy. So that's plus minus, so that would be a 3 times the remaining determinant. If I take away the first column, second row would be 1, 3, 1, 2. So we would get 3 times 2 minus 3 over negative 8, or 3/8. And that is Cramer's rule. Let's make it a little smaller so we can see the whole thing at once. And that gives us the x1, the x2, and the x3. What I'd like to do next is show you the proof of this Cramer's rule. So let's go ahead and do that. I would like to do this for a general n by n matrix. So I'm going to let A be an invertible matrix where A is written as a set of vectors of an vectors, where each ai is an Rn, so that makes it an n by n matrix. And I is equal to E1, E2, dot, 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 all the way to En as we have defined it before. So we're going to look at AX equals B. And I'm going to take, instead of A times X, I'm going to take A times I, this matrix of IX, using the same notation for A of I of B, but now it's just I of B of X. So what does that mean? So we're going to leave A alone. I'm just going to figure out what this new matrix is. That means I'm going to have here E1, E2, right? Dot, dot, dot. In the ith column, I'm going to put that vector X. And then, by definition of multiplication, this is just AE1, AE2, dot, 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 AX, and then AEN. And again, this is the ith column. And since AX equals B, that's just going to be a B. And AE1, that means we're going to take the matrix A and we're going to multiply it by the vector 1, 0, 0, 0. So that is going to end up being the same as A1. That's going to be our first column of our vector, right? Because you take all of A and you multiply it by 1 with a bunch of zeros. It's just going to give you that first column. And so for this one's going to give you A2, and this one's going to give you AN. And by definition, that is just AI of B. So what do we have? So we have that the determinant, I'm going to look at the determinant of each side, of AIX better equal to the determinant of A, since they're the same. What I'm going to do here is I'm going to use the determinant of A times B is the determinant of A times the determinant of B, where the B is that second vector. And I'll just rewrite this. And then I'm going to solve for the determinant of I of X. And then you can see that we almost have it. This is just going to be Xi. And then we get our formula. Why is that going to just be Xi? You will see it's Xi if you make a cofactor expansion along the ith row. Here's what I sub I of X looks like. Again, we replace the ith row. This is, the ith column by X, and all the other ones are just E1, E2, so forth. So if you figure out this determinant in the ith row, these would all be zeros except for X sub I. And X sub I would be plus because it's along the diagonal, plus, minus, so forth. And the determinant left over would just be the identity matrix, because we would take out all the x's, and what's left over was all 1. That would be actually the identity matrix n minus 1, but it would be 1 regardless. So it ends up getting just xi. So we have the formula, and if you look here, you can see that is a nice proof of Cramer's rule. And that concludes this video.